we're going to talk about an important application of matrix multiplication. The row operations and the Gaussian elimination process we use to solve AX equals B, row swaps, row scale, and row replacement, all of that can be done with matrix multiplication. Now, the key behind all of this is that we need to define a special kind of matrix called an elementary matrix. An elementary matrix is a square matrix, we'll just call it E, that's the result of performing just one row operation on the identity matrix. The identity matrix is a square matrix composed of zeros and ones. Now, here we're just going to look at the 3 by 3 case. The reason this is called an identity matrix is that if you were to take this matrix and multiply it by any other matrix of compatible dimensions, it should just return the original matrix. So for example, if I just take this simple matrix multiplication and however you want to perform it, what you'll find is that the 1 in the identity matrix will simply return every entry. This is why it's called the identity. It returns the original matrix A. It doesn't really matter what order you do it in. So let's take a look at how we're going to construct our basic elementary matrices. Our first one we'll consider the row swap matrix. So let's say that we want to swap rows 1 and 2. We are going to perform that operation on the identity, and we're going to call this elementary matrix E, and all we're doing is swapping row 1 and row 2. And this is our elementary matrix. Let's take this elementary matrix and multiply it by the matrix I had above, the 1, 2, 3, 4, 5, 6, 7, 8, 9. If you go ahead and you do this, you'll get a 4, 5, and a 6. So remember, you'll be taking this top row, turning it sideways and doing a dot product with each of those. It'll pick out the middle row of A. Now, similarly, if you talk about this entry here, it'll pick out the top row of A, turning this sideways and doing a dot product will pick out the bottom row there. So in general, if you want to swap rows I and J, what you're going to do is just swap I and J in the identity to get your elementary matrix. So the row swap matrix is pretty straightforward. Same thing with the row scale. For example, let's say I want to scale the second row by 5 and turn this into the new second row. So I have to perform this operation on the identity to get the elementary matrix that I want. So let's say I want to compute EA again. So I'm going to take the identity matrix, and the only thing I'm going to do to it is scale the second row by 5. Everything else stays unaffected. If we do the dot product version of computation for multiplication, we'll get a 1, 2, 3. Now when we turn this row sideways, we'll pick out the middle row of A, but we multiply everything by 5. So in general, if you want to scale the ith row by k, you just multiply the ith row. Finally, the one that's most useful is going to be row replacement. So let's say we want to add -4 of the first row to the second to make the new second. The elementary matrix, we want to leave the top row alone. But what we want to do is now alter the second row. So we're going to go to the second row and perform this row replacement. We want -4 bunches of the first row, add to the second row to make the new second row. If we again do the dot product version, we take the top row of E, turn it sideways, and dot product will pick out the 1, 2, and 3. Now if we turn this row sideways and we do a dot product, we're going to get -4 bunches of the first row, and that's going to give me a -4, and it's going to add to 4 bunches of that second row, which will give me a 0. So when we continue to do the dot product and we apply it to this second column, we'll get a -8 plus a 5, which is a -3. When we apply it to this row, we'll get a -12 plus a 6, which will give me a -6. If I continue on and do the dot product multiplication, no difference there. For example, now let's say I want to take -7 bunches of row 1 and add it to 3 to become the new 3. So it's the same idea. The top row is unaffected. The middle row will be unaffected. The only values we want to change are for the new third row. So we're going to take 7 bunches of the first row, none of the second as before, and then add it to that third one. And the reason we're picking -7 is because we're trying to create zeros underneath. Let's call this E1. So there's E1. And now we're going to apply an E2. So this result was E1 times A, and so now we're going to apply an E2 times this. We take the top row of this dot product, turn it sideways. By design, leaves that top row unaffected. If we take this middle row and turn it sideways, it leaves whatever middle row is there. We want to take this row, turn it sideways. So we'll have -7 times 1, 0 times 0, and then +7. So that will zero that out. We'll get a -14, a 0, and an 8. So it'll give us a -6. And then we'll get a -21, a 0, and a 9, and that'll give us 12. To put it all together, when we say that we are going to row reduce something to a row reduced echelon form, what that means is that we are going to take the matrix A and perform a series of matrix multiplications. They all get applied multiplying on the left. We keep going until we hit this row reduced echelon form. So if we take a look at this example, so we have E2, E1A, and it's 1, 2, 3, 0, -3, -6, 0, -6, and should be a -12. Sorry, I forgot the sign here. This isn't in row reduced echelon form. So now what I want to do is I want to scale this second row by -1/3, and that's going to become the new row 2. So I'm going to construct a new third elementary matrix to do that job. And the elementary matrix, by definition, just says apply this one operation to the identity. When I go ahead and do that, the top row will be unaffected. If I take the second row, turn it sideways, do the dot product, 0, 1, 2, we're one step closer. We've located this pivot in the second column. So now what we want to do is do a row replacement to get rid of this thing. We're going to take a fourth matrix. We want to take 6 bunches of the second row, add it to the third row to make the new third row. Okay, so we are going to leave the original first row. We are going to leave the second row, take +6 bunches of the second row, add it to the third row to make the new third row. And we're going to put this answer here. So again, just to kind of belabor the point here, I'll show you how it goes. 0, 1, 2. We're going to flip this row sideways, do the dot product. You'll have 2 times 0, 6 times 1, and 1 times -6, which by design will give me a 0. I will get a 0 and a 12 and a -12, so it's a 0. So the last step that we need to do is we want to take -2 bunches of 2, add it to 1 to make the new one. So this is where it's a little different. We want to change row 1. So the new row 1 will be like this. We want to keep the original row 1. We want to take -2 bunches of row 2 and 0. And the rest will be unchanged. We'll have 1, 2, 3, 0, 1, 2, 0, 0, 0. We perform this multiplication. We'll have a 1. We're going to turn this row sideways, do the dot product. We'll get a -1. All the other rows will remain unchanged. So if I take this multiplication, turn it sideways, 0, 0, 0. And this is in row reduced echelon form. We have these two basic variables and we have a free variable. So this matrix right here is going to be called U, our row reduced echelon form. We had 5 elementary matrices to turn this into U.